we go. All right, so the purpose of today is to take the results that we got from the lab, and match them to equations that will benefit us that are the exact same purpose of the lab. Look at all these variables happening when an object is constantly accelerating. Remind me real quick, I know I didn't have this on the bell ringer, but I think it's going to come up a little bit later. When you did the other lab in here, position versus time for the car, okay, what shape did that make? Made linear. More than likely, it looks something like that. Yes? We'll come back to that a little bit later. Right, now, let's actually do the bell ringer up here. Are you just off to the side? Very good. Okay, the first one says, what's the relationship between these two look like? What is it? Parabolic. Very good. Okay. The next, average velocity versus time is? Linear. Correct. Okay. And instantaneous velocity versus time is? Linear. Okay. And then finally, instantaneous velocity versus time is, sorry, not time, because time would be the exact same, versus delta x is? Square root. Okay. Now, Wes asked an excellent question of, okay, is v by itself typically considered constant, or can I just use it as velocity? Very quickly and early on, you're going to start me seeing using v as kind of just velocity, but when I do a given and find, same thing as before, if I just write v, I'm going to write it, that's constant, okay, because I'm going to use I and f and all those sort of indexes if they're changing. Why, looking at this, do I really not need to write instantaneous? Very easy. Why do I not need to? Why can I do this and know that you are not going to assume it's constant?
Because it's not very.
It would be horizontal on all of these graphs. You can clearly see it's not. You can clearly assume that this is talking about the velocity at a specific time, because the velocity at a specific time, as clearly seen from the graph, is changing. Yes, and at different positions is of course changing. Now, if we reverse the lesson that we did last week. Last week, I gave you all these equations and said, all right, what should they look like? Imagine we go to the lab, which you did, okay, and we got this data, and the graphs look like this, which you did, okay? Those should have very specific equations that go with them, right? Meaning, what is the generic equation for the parabola?
X squared.
Give me the whole thing, please.
Y equals kx squared plus b.
Correct. So my y variable is equal to something times my x variable squared plus b. And we can look at this, we can look at these results. Hopefully you've actually found the equation and you kind of know what this exactly is supposed to be. But for my purposes right now, I can just change that to more specifically what we're doing simply by just changing the variables from y and x. Meaning this data in the lab, okay, which I did not affect one way or the other, you measured, you saw what it was supposed to be, okay? I'm not doing that, the book's not doing that. Reality told you what the answer was supposed to be. Reality told you it should look like this. And reality says that if this is the case in real life, that the equation that we should come up with should be delta x is equal to something times delta time squared plus something, but in this case, more than likely, 0. Does that make sense? So if I come up with an equation today, it should match these results from the lab. Yes? Please do that for the other 3. Okay? Meaning, I wrote the generic equation of the line, so these are like the specific results of this line.
Okay.
Should take you, like, if you understand what I'm saying right now, like a minute to do. Please don't take long. If you don't understand, I'll say it once again. I'll do it for the second one. So this is a line, so what shape should I, what's the generic equation?
Y equals mx plus b.
Try again. Y equals kx plus b. And so all you do is you just, very simple stuff. Okay, what's my y?
Average velocity.
Average velocity is equal to, I put question mark, you can just write k. It just means I'm putting question marks here to be like, it's something, I don't know what it is. But something times delta t plus something, which is more than likely, in this case, in our lab's case, whatever it is, was more than likely 0. We don't know it's 0, but we're pretty sure. So do that for the other 2 real quick. I'll give you another 30 seconds. We'll be right back after these messages.
Did you start recording?
Yes, I did. Did you know I started recording and just said that so that it was on the recording?
You can see that it's
Don't
recording.
forget
to start recording tomorrow.
But you need to do the
Listen to the recording and then
sync
jump
the audio.
You got stuff to do. Stop telling me what to do. You've already got things to do.
Here's the plan. You're gonna listen to this recording.
You got this done?
tomorrow. What?
You got this done?
Yeah.
Okay. Then you can continue. I was gonna say that stop talking. I was kind of expecting you to say no, but you said yes. So, okay, yeah, my apologies. Keep going.
Teacher Spain hour. Don't forget to start recording.
I don't watch these
You're
videos.
gonna. That's the plan
How
now.
do I watch these videos? You watch these
Wait,
videos.
it picks up audio. No, you're supposed to.
Yeah.
Can you hear us right
What
now?
if I remind?
Yeah, 100%. Everything you're saying.
What if I remind myself?
Hey,
Don't be
to-
like, I need to put this on YouTube.
Shout out to the kid
Hey.
who's not here today and is watching this at home.
Fair enough. All right, moving on. What do you get? So let's skip this first part. What should the final results be?
Shout out my mom.
Your mom's gonna watch this? All right. Okay. What's the final? Come on. We got too much to do. Trust me. We're gonna get to the end of the day, and you're gonna be like, I wish I had more time. Start being nice to your future self. What's the equation?
Average velocity.
No, not in this case.
Oh, velocity equals.
Technically
K
instantaneous.
delta t plus b.
Yeah, something. Yeah, which you put k, leave k, just fine. Times delta t. Technically, is sort of delta t plus something. Okay. Next, what's this guy?
This one was
Instantaneous velocity equals
Something.
The square
Square
root
root
of
of
delta x.
x plus.
Okay. I do this every year, and I think that students are sitting there kind of like rolling on it. This is the easiest thing. Why is it helpful? I think it'll come back, and you'll see in just a minute. All right, here we go. So the purpose of today is to develop equations. They're known as, and this is kind of the title of the notes today if you want, they're known as the kinematic equations. Now the kinematic equations, we technically already have a kinematic equation. Kinematics means the description of motion. Okay, so technically any equation that describes motion is a kinematic equation, but specifically, usually this phrase will be used to reference these specific sets. And these specific set come with two major assumptions. Well, one major one and one minor one that I will ask you like 1,000 times in your physics career, even if you come to physics 2. I think I did it the other day in physics 2. What were the assumptions behind the kinematic equations? The first one I'll tell you is this. We've already said it in here. The first assumption is acceleration is constant. That changes how some of the results come up here. Write that down somewhere. Acceleration, kinematic equations, is constant. The second one is a minor one, and in general kind of applies until we get to chapter 4 and forces, and that is we are going to ignore air friction. Now, air friction is definitely there, albeit you can actually see from how good your lab results are, and I would guess that most of your guys' lab results are pretty darn close to, if you did it well, you should probably be seeing oh my, this is really close to perfect data. It's usually very, very good if you've done it well. But so from that good data, you can go, well, that means air resistance probably did not affect this in any major way. If it was affecting things, we'd probably get something weird with the shape, blah, blah, blah. So those are the two major assumptions in kinematics. One, the biggest one, acceleration is constant. And I'll probably ask that again today. So make sure you have that down somewhere. And number two, kind of a minor one that'll happen until chapter 4. We're going to ignore air resistance. Okay, next. What are the equations that we have so far?
Slope intercept or y? Slope intercept.
Physicsy equations, kinematic equations, not mathematical ones.
Displacement equals x final minus x initial.
Again, that's also kind of a mathy one. You're not wrong, Eli. You're doing great. Okay, great. Sorry, less than Eli. Backwards here, my apologies. So, no. Just I'll give you a hint. There's two of them that are definitions, the basic definitions of concepts, and a third that we'll talk about is kind of an extension. Nick, you had a hand up a second ago, no? Or was that just you saying hi? My son does that too. It's fine. Okay, my bad. All right, anybody else? Definitions. Two definitions.
Wait, definition.
What's the definition of velocity?
It's delta x over delta t.
Yes.
And acceleration is
Thank
delta
you.
v over delta t.
There's your two definitions that we're going to start with. Okay? I will talk about the third extension of one of those in just a second. But these are the two equations essentially you have right now. All right. The first equation is pretty darn easy. And actually, in all seriousness, it is basically just this equation. It's this equation rearranged. So it's good to know that the first equation is literally just this rearranged. We're going to talk about a couple of subparts within it. To start off with, Grant, since you started me really well a second ago, let's do it again. What is the change in velocity, Grant? How do you get the change in velocity?
X, or velocity final minus
Thank you very
velocity.
much. Final minus initial. The change in anything is final minus initial. So all we're going to do for the first kinematic equation is we're going to take this equation and we're going to solve for VF. To which you go, why we could solve for any of them. You're right. I think you'll see why at the end, just with a little guidance here. Okay, this is where it is. But again, this next kinematic equation is this equation. So could I get to the same spot if I just start at the definition of the acceleration? 100%, and sometimes it's vastly easier. In this case, I don't care if you start at this spot or the other one, so keep that in mind. All right, this algebra is relatively easy. Usually I do this really quick, but I want to show you an intermittent step. If you were solving this for VF, what is the first thing that you would do? Don't worry about the middle piece right now. Let's just go with these two sides.
Figure out what VI and delta T are.
No numbers here. It's all variables today.
Then you have to get,
Times by time.
Isolate VF.
Yeah, generic stuff. If you're not great with algebra, or if you don't great with algebra with variables, is get rid of the fraction first. Always. So let's multiply by delta T on both sides, and we end up with this. Now, the reason I want to highlight this is specifically to show you something in a second, and that is that, keep in mind, that equals means, of course, equivalent to, or both sides are the same. And we just said a second ago that VF minus VI is what? If I wanted to fold this back in.
velocity.
Yes, the change in velocity. A lot of equations, by the way, in physics, kind of like sort of like transformers. They kind of like pop out and go back in and kind of to help us understand the concept. So keep that in mind. But yeah, so this is delta V, which means this must also be delta V. Yes?
Yeah.
They're equivalent. And that should make sense because acceleration, by definition, is this ratio, the change in velocity over time. And if I took this ratio and multiplied by delta T, I'd be left with just delta V, right? So this is the equivalent to delta V. Cool with that?
Yep.
All right. The last algebraic step is pretty easy to isolate VF. What do I do?
Wait, what?
Add the on the other side.
Just add VI on the other side. Very good. And I'm going to rewrite this kind of just so I can isolate. I'll do the mathy thing of putting the variable on the left side. This should be VF. I'm adding this over here, but I'm writing it over here. Does everybody see? I'll do this. Okay, yeah, so this is VI plus A delta T. That is your first kinematic equation. And you know what? I'm going to write this down. If I have like spaces on the page, if I were you, I'd write this down in like the third space.
All right.
Now, two things about that equation. Number one, what did I say just a second ago A delta T was? Equivalent to.
Change velocity.
So this equation basically says, hey guys, if you want your final velocity, take your initial velocity and add how much has changed.
What?
It's really, really simple in all honesty. Okay? Meaning, hey, if I'm going at 8 meters a second and I change by -2, how fast should I be going? 6. That's what that equation ultimately really says. But keep in mind, like I said, as you just saw, that equation is that equation. Yes?
Yeah.
So can I start from both spots if I have a problem with these variables? 100%. The second thing that I want to highlight here is in the lab, what did we set VI to be? What do we set your initial velocity in the lab?
Yeah.
0. So if this was your equation, monitoring stuff in your lab, and I then said, hey, let's predict what this shape would be, you'd have velocity f, or instantaneous, right, relative to time. And what equation would this, what shape would this make? It'd make a linear shape. And what would the slope of that one be?
In variables?
Acceleration, right?
Yeah.
So the acceleration of this, the slope of this graph would be acceleration, and the y-intercept, given that VI was 0, would be
0.
Which is quite literally exactly what we got on the lab, yes? That velocity instantaneous is equal to something times delta t plus 0 because VI was equal to 0. So good. So the first equation matches exactly what you already have from the lab. Let's continue. Now, about this equation, kinematic equations are made up of 5 distinct variables. Okay, right? Sorry, 5 distinct variables. Right. Currently, you see 4 of them up there. As a matter of fact, all of the individual equations are only made of 4 variables. So you can see VF, VI, A, and T, that's 4 of the variables. The other one's going to be delta X in this particular case. Now, let's talk about, I said a second ago, that this guy right here, let's draw a line here. I'm going to switch colors here so you know I'm dealing with some other equation right now. Let's go this guy right down here. As a matter of fact, let's re-change this guy right here. The definition. Technically, this is not the definition. Well, it sort of is the definition for constant velocity, but really, in truth, this is starting off at the average velocity. Yes?
Yes.
Because constant and average are the same. Because if you are constant, it is the average. Now, there is another thing. There's another equation we can use for average, albeit there's several times I told you you couldn't. What is the other equation that you could use for average?
Absolute value.
Add up all the velocities and divide by the amount of velocities.
Correct. When I did the dumb example up front, which I've referenced, I believe now at least the 5th or 6th time right over here, where I was going at 2 and then at 0.5, I told you you couldn't take 2 plus 0.5 and divide by 2 to get 1.25. Why? Why couldn't you?
Because you didn't spend like equal amounts of time.
Equal amounts of time in those particular cases. However, since we have at the very beginning here made sure to say acceleration is always constant, will this graph over here always make a straight line? Yes. It will always increase at a steady pace. It will always make a straight line. It will always be linear. I've actually drawn this graph once already for you, albeit you didn't necessarily know that's what this is. And average velocity should go right about here. Yes? Which would hit right about here. Meaning, if the max was 4 and the initial was 0, the average should be 2, which of course you just got by taking 0 plus 4 and dividing by 2. And why is it completely okay to use here with a constant acceleration where it wasn't before in the example over there? No. The amount of time before that point and after that point is completely equal. And it will always be equal because acceleration is constant. Meaning this, acceleration is 2 feet per second squared. What does that mean is going on?
Every second he's going, wait.
Every second.
He's going at velocity.
Not that's velocity. If I said velocity was 2 feet per second, you'd be right. I said, what does it mean if acceleration is 2 feet per second squared?
Every second his velocity changes by 2 feet.
So that would mean in 1 second, it'd be going 2. In 2 seconds, they'd be going, okay, I'm going to do this twice more. And another second, it'd be going 6, right? And then in 4 seconds, you'd be going 8. So was half the time spent below 4?
Yeah.
And half the time spent above 4.
Yeah.
So is 4 100% the average?
Yeah.
In other words, if you divided this up intermittently too, if you went like 1, 2, 3, 4, all the way up to 8 and divided by 8. Hi there, how are you today? Much. I appreciate you.
You guys stare at me.
No, of course not. There you go. Thank you so much. You have a good day. All right. If I divide it up intermittently, it doesn't matter how you divide it up. Like I divide it up 8 times, or 16 times, or 32 times. However you want to divide it up, you're always going to find the average is 100% 4. Meaning, if acceleration is constant, which we said for the kinematic equations it always will be, then the average can also be VI plus VF over 2. You cool with that? Cool beans. All I'm going to do now is I'm just actually not going to worry about, well, if you were going to take this left side here, just this piece right here, and solve for delta x, you would get delta x equals average velocity times time. I imagine you've done this equation or shown this algebra at least half a dozen times, if not a dozen times, in the earlier parts of the chapter. But I just said a second ago that average is also equal to this. Yes? Yeah. So I can substitute it in here, and the equation would become, as a matter of fact, let's just go ahead and write it over here. The next kinematic equation, which I'm going to write in the first spot, delta x equals average velocity, aka that, times time. And now I've got a kinematic equation that has brought delta x into the fold. So I now have the 5th variable, and you'll notice once again, it's made of 4 variables. As a matter of fact, humor me with this. Let's move you over to the side, buddy. I don't need you right now. Okay. Which of the 5 variables is missing in the first equation? Acceleration. And what about the third one? Delta x, which makes sense. I just said I was going to add it back in. There is going to be a missing one, which will kind of come up a little bit later. Probably a little bit more tomorrow, but we need to have this in the notes. All right. Now, we need to find the other relationships. As a matter of fact, if you look at both of those 2 relationships that I've established so far, delta x versus delta t will make what shape? Linear, but that is weird because that would assume that in a lab, average velocity is constant. Is your average velocity constant in your lab? No, so we would definitely not get a linear function right here. Okay? We got 2 nonlinear functions, but we've not yet seen equations that go with this. Let's back it up just a second. Go back to this slide right here, and something I asked you at the very beginning, and ask a very important question, and it is this. In your first lab, this guy right here, it made a linear function, which you've already told me. Why? What about the lab caused it to be a linear function?
The velocity was constant. There was no change.
Velocity was constant, absolutely. And if you look, actually, what is slope, by the way?
What?
What is slope? In general, sorry, someone said it, I thought. Change in...
Rate of change.
Right, so change in y over change in x, right? What is on the y here? So here's what I'm saying. Slope in y is this. What's on the y? And what's on the x? What is change in x over change in t, guys? Which makes sense, because what you said to me a second ago is that, and we remember this from the data analysis, the slope of this line is the velocity. And it makes sense that the slope would be constant because the velocity is constant. So let's ask the more important question. In the ramp lab then, why does it make a parabola? That's the starting answer, but I think there's more that we want to unpack there. I 100% agree, and I think that all the answers within that, but let's completely unpack that. Because the ramp is accelerating, which is 100% the right answer, but I think there's more to it. Okay, because it's accelerating, what's the car doing? Speeding up. Because the car is speeding up, what's it doing? What does it mean if one car is going faster?
It's going
velocity
more distance higher later than it was before.
We'll say that again, Wes.
It's going more distance later than it was.
Displacement, but yes, he's pretty much fine. Okay, so more displacement in the second than it was in the first second. And more displacement in the third second than it was in the second. Or to show that kind of visually, how did I lose all of them so far? Here we go. Okay, to show that again visually, watch here. If I just choose an arbitrary amount of time and look at it at 2 different spots on the lab, arbitrary meaning whatever the heck you want, that's delta t and that's delta t, and instead then look at that change in x, this is a visual representation of slope. And you can see that those 2 triangles are completely identical because of course they are, same amount of time, same amount of displacement, same amount of slope. If you do that again for this graph, where I choose an arbitrary amount of time, do you get the same effect?
No.
Because of what you just said. Because it's going at a higher velocity, okay, it should be covering more displacement, more displacement, more displacement. Cool? All right, now let's get into the math. Now, how do I get to the math? Or how do I get to the results from that whole mess? What we're going to do is we're going to start at those exact same 2 equations that we just had. As a matter of fact, these 2 right over here. I'll grab these. Hopefully I grabbed all of it. Copy, new page, paste. All right. Now I got some extra stuff. We'll get rid of that in just a second. Don't worry about it. All right. So what we're going to do here is we're just going to do honestly, some very basic substitution. Okay, we're going to look at what these variables look like in a way that, so we'll just take this guy right here. Actually, let's use a different color so you see what I'm doing. Okay, I'm going to take VF right here, and I'm going to substitute it in for this VF right here. We've already seen that both of these equations are in fact true. This one developed from the equation for acceleration. This one developed from the 2 equations for average velocity. So now we're just going to combine the 2 together to see what comes up with. So basic substitution here, but I'm going to use colors to highlight it. I'm going to rewrite absolutely everything, okay, except when it comes to this, the VF, I am substituting in not this, but this piece right here. So it's not VF anymore. VF is equal to this. So let's substitute that in right there. Does that make sense?
Yeah.
Okay. So these two equations are identical. The only difference is instead of VF, we have that right there. And now all I'm going to do is quickly simplify. If I asked you to simplify this equation, okay, what would you, let's use a different color, by the way, for this math. Please make sure you're doing this math. Please make sure you're along with me right here. A lot of this is practicing algebra and simplification, which you 100% are going to want those skills as we continue on with this. But what would you do first to simplify this? Combine the VI's. 100%, that's 2VI. I'm just going to go ahead and put an equal sign over here because delta x is not going to change. Okay, so 2VI plus a delta t, the whole thing divided by 2 times delta t. What do you want to do next?
I would say put the delta t on top of it.
Put the what?
Distribute.
Distribute delta t is what you're saying? Just as a heads up for anybody that's watching this from first hour. First hour we did the opposite way. Doesn't matter. We divided by 2 in first hour. You guys want to distribute first. There's not a problem one way or the other. But yeah, let's distribute. So I got 2 VI delta t plus a delta t squared all over 2. To which I would argue there's probably one more simplification you should make.
Get rid of the 2.
Yeah, and remember that to do that, we just reminded ourselves what we talked about kind of a couple lessons ago, and that is just a shortcut for dividing both things by 2.
Yeah,
right?
both.
So, final equation, we would get this. Delta x equals the 2's there cancel, giving me VI times delta t. And I could divide this by 2. I think it's cleaner, actually. It doesn't matter because they're the same. But I think it's a little cleaner, actually, to just put a 1/2 out in front. The 1/2 is just dividing the whole thing by 2. Yes?
Yeah.
And this is our third kinematic equation. Now, I have sad news for you, because people usually, from year to year, look at this equation, and they usually say, holy crap, that's a complicated looking equation. Okay? And then what they then followed up by saying is, I'm going to avoid that equation like the freaking plague. And I got bad news for you. That is probably easily the most powerful and most used equation in this particular chapter. To prove it, remind me real quick, in the lab, what was VI?
0.
0. And if this equation had a VI of 0, what would happen to that entire term?
It would get rid of this.
It would cancel out. And then if I said, just completely arbitrarily, just for no good reason whatsoever, let's pretend we were graphing delta x versus delta t for this equation. What shape should delta x versus delta t in this equation make? Parabola, right. And what would the k value of it be? 1/2 times a. So if you were to theoretically be in a lab, then it would be something like delta x equals 1/2 a times delta t squared plus, well, 0, but only because VI is 0 in this particular case. Is that reasonable for you to get lab results and say that it would kind of match perfectly with that equation? Yeah.
I'm rocking with it.
So that equation right there was already tested. What would the missing variable for that guy be? Out of the 5, which one's missing?
Velocity line.
You'll note, by the way, the easiest way to spot that is what did I use to substitute? Because that's the one that went away. All right, last thing of the day. Got about 5 minutes. I think we're rolling well here. Just a minute ago, I substituted VF in here. We're almost going to do the exact same thing. Let's just grab these again.
Number 4.
Yep. Oh, who knows? Maybe I'll mix it up. All right. Now, the first thing that we're going to do is actually, we're going to take this equation, because if I just put delta x, well, I can't really substitute delta x in here. There is no delta x down there, right? So what I'm going to do is I'm just going to take this guy and solve for t. Now, there's a couple of ways that you could do this simply, but here is the quickest and most efficient way of them all. As complicated as that is that a fraction?
Yeah.
So I can just take the reciprocal, knock it out, and multiply the reciprocal on the other side, and we'd be good.
You made an equal sign.
I did, utterly and completely accidental. Look at that. All right, so this flipped would look like that, yes?
Yeah.
And then it would cancel over there, and then I'd multiply by delta x, so I'll just put that there. And that would equal delta t. And now we're going to take that and substitute it right here. Make sense? Here we go again. All on our own. Down the only road we've ever known. Like a twister. We were born to roam alone. We done made up our mind. Sorry. All right, so I'm writing all of the exact same equation. The only difference is right here. Delta t is delta t, and delta t is that. So I'm going to write in that whole crazy mess. Oops. That was dumb. That was not an A. That should be a delta x. And this looks icky. It's very icky.
It's icky when you say icky.
But 100% it is. Shows we don't like the word icky. So I shouldn't say it very much.
I think you should say like weird.
Icky, icky, icky. All right. So, like I mentioned earlier, if you deal with something and you're like, this algebra looks crappy. I've said this 1,000 times. Well, not 1,000. That's a little bit hyperbolic. Different type of hyperbolic. Sorry. I hope you're not homophobic. All right. So, what do we need to do to simplify this? If things are complicated, I've said this a bunch. Get rid of the fraction. 100%. As complicated as it looks, get rid of the fraction. What do I do to get rid of the fraction?
Multiply by the...
Right there. Here's what people usually screw up. They'll do this, which is correct, and then they'll stop, which is absolutely screwed up. Because when you do that, students get this idea, I do it on the left side, I do it on the right side. No. The rule is you do it to every single term that exists. So, by the way, just to show you that real quick, here. Real fast. Let's go. 3 equals 1 plus 2. Can I just multiply 2 here and 2 here and they are equals? No, that's not how that works, 100%. So keep that in mind because despite how intelligent you are, that is one that a lot of students your age make a mistake on. So all I got to do is multiply this term by the same thing as well. And while this looks complicated, as you simplify this process, I think that you'll find that it's not that bad. For starters, what does this become as we distribute? Excellent point. Velocity initial. What's that? No, you're missing a 1. This should be velocity initial times velocity final, right? Distributed here, plus VF squared. If you said that, I apologize. I misunderstood you. All right. Next one right here. Redistribute again. What do you get? VI squared. All right. And then finally, you can, algebraically, you can position these however you want. I'm just going to position them in the way that is the most common in physics text, so you see it. You could delta x first, then a, then 2. Who cares? But this is how it's usually written. 2 goes out front, followed by a, followed by delta x. And that looks messy until you realize that what's going to be nice about the VI-VF, as they are the same on both sides, they will cancel. Leaving us with the final kinematic equation. VF squared equals VI squared plus 2a delta x. And remind me real quick in the lab. Sure, there's no reason for this. What was VI? 0, and that would cancel that out. And then if I wanted to solve for VF, for example, here, humor me, I'm not done. Okay, what would I do to solve for VF if this was 0? I want to solve for VF. Come on, what is it? Is it by itself right now? Square root. So you would get VF equals the square root of 2a delta x, which is the same thing as VF equals the square root of 2a times the square root of delta x. And then if I grabbed you to graph instantaneous velocity versus delta x, what shape would that make? Square root, the slope of which would be the square root of 2a. And if you look at our results, you get... There you go. We will use these a bunch. Oh, last thing that's up here. What's the missing variable for the last one?
We're going to go with... Wait, hold on.
It's
Delta t. Correct. All right. See you guys tomorrow.